Hello viewers, this is Walgo now taking you through the story for A-Level Physics Paper 1. And this video we're going to go through the topic of Newton's laws of motion and friction. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. Before we proceed, let's first look at the course outline of this paper. So physics paper 1 is divided into 3 parts. The first part is mechanics, where 4 questions come from these topics. The second part is heat, where 3 questions come from these topics. And the third part is modern physics, where 3 questions come from these topics. So what is the topic which is ticked means they are available on this platform. And the ones which are not yet ticked means they are yet to be uploaded. So we are now on the section of mechanics, and video 1, 2, 3, and 4 are already on the platform. And now we are going up to video 5, which is Newton's laws of motion and friction. I encourage you to watch the videos in the order of the numbers as listed here. 1, 2, 3 like that. Don't say let me first watch video 5 and then I go to video 2. That is not okay. And the reason is because the knowledge got from the previous video or the previous topic may be helpful for the current topic. And on this platform, we are interested in the calculations, but complete notes are available in the books we recommend. So Physics 1, we recommend this book, Mastering A-Level Physics, Paper 1. It contains notes, worked examples, and try questions on all the topics of Physics Paper 1. So for orders of this book, contact the author on any of these 2 contacts. Then for Physics Paper 2, we recommend that book, and Physics Topical Question Bank, we recommend that question bank. It is topical and it has answers, and it has a number of years ranging from 2022 to 1992. So I believe these 3 books will do you good. So now we shall start our topic, Newton's laws of motion and friction. These words are not strange to you. I think you saw them, you looked through them in your O-level physics. But now we are going to go through them and also add on something that can make the topic suitable for A-level. So this topic of Newton's laws and friction is all about the relation between force acting on a body and its motion. Remember the previous topic, for example, projectile motion, motion in a straight line. There was motion, but we were silent on the forces acting on the particle. We didn't mention anything about the forces which cause the particle to move. We just said it moves, and we wrote the equations of motion, and we used those equations of motion. But now in this topic, we are going to be mindful of the forces which cause that motion to occur. So this relation was Newton who first understood the relation between force and motion and put forward 3 laws governing the motion of bodies after a series of experiments. So shall look at those laws bit by bit. Let's start with law number 1, or what we call Newton's first law of motion. So Newton's first law of motion states that a body remains in its state of rest or continues to move with uniform velocity, note this word uniform, until it's compelled to act otherwise by an external force. So here in this topic, we shall be interested in motion due to these external forces. That was first law. What about second law? Second law states that the rate of change of momentum is proportional, or you can say directly proportional, to the applied force that takes place in the direction of force. Remember, we are interested in now motion when there is a force. So those two words will be more common: force and motion. So this law can be expressed mathematically in this way: force proportional to change in momentum. This is the final momentum. Mass times velocity is momentum. So final momentum is mass times final velocity. Initial momentum is mass times initial velocity. And t is the time taken. So to remove this proportionality sign, you need to include a constant of proportionality, which we shall call k. And experiments carried out by Newton show that the value of k will be equal to 1. And therefore, it gives you this formula that F is equal to change in momentum over t, where F is now the average force. So there are some definitions which we shall need to define. One is momentum. We have already said that momentum is the product of mass and its velocity. Then the other one is called impulse. So impulse is the product of force and time. So when we multiply force by time, we shall get impulse. But remember, in the previous slide, we saw that F is equal to change in momentum over t. Therefore, when I bring this t this side, I'll come up with Ft being equal to change in momentum. That means that if they ask for impulse, you can either get impulse by multiplying force with time or by getting the change in momentum. So that is the reason why the SI unit for impulse, they are two. One is Newton second, which is good from here. Force Newton T is second. Another one is kilogram meter per second. So kilogram is for mass, meter per second is for velocity. So any of the two SI unit is okay when they ask for impulse. And with those two formulae, we can go through these questions. Question 1 came from UNEB of 2000, paper 1, question 1C, and it says, a ball of mass 0.5 kilograms is allowed to drop from rest from a point at distance 5 meters above a horizontal concrete floor. Okay. When the ball first hits the floor, it rebounds to a height 3 meters. Roman 1. What is the speed of the ball just after the first collision with the floor? Okay. Roman 2. If the collision lasts 0.01 second, find the average force which the floor exerts on the ball. So here we shall need to make a simple sketch. So we shall have our ground or concrete floor, then we shall have the ball at a height of 5 meters above the ground, which is this. So they said it drops from rest. That is why the initial velocity is 0. Then they said when the ball first hits the floor, it rebounds. So it will move until it hits the floor with a certain velocity which we don't know yet. That is why we are putting a question mark, because we don't know that velocity yet. Then they told us it rebounds. So at this point it will now rebound with a velocity which we don't know. After, remember, the collision lasts for 0.01 second. So after 0.01 second, that is when it rebounds. And it will rebound to a height of 3 meters. So that means that here it is momentarily at rest. That is why the final velocity is 0. So with that sketch, we can easily answer the question. First they said, what is the speed of the ball just after collision with the flow. So they want the value of this, because V1 is just before collision, then U2 is just after collision. So using the third equation of motion, and for motion CD, that is up on rebounding, which has come out so that the final velocity, remember it was 0, initial was U2, and G is constant 9.81, and S is the height, which was 3 meters. Therefore, you come and simplify and make U2 the subject. That will be the velocity just after collision. Then Roman 2, they asked for, if you look at Roman 2, they said if the collision lasts 0.01 second, find the average force which the flow exerts on the ball. Remember, average force is change in momentum over time taken. So the time taken here for it to hit and again rebound is 0.01, which is already known. And now the final velocity at rebounding is U2, and the initial one is this one, which we don't know yet. So we have to first calculate V1 so that we can be able to get the change in momentum. So we shall come here and look at motion AB. So for motion AB, we have V1 final velocity, which we don't know. U initial velocity was 0 because it was dropped from rest. G is 9.81, and this is the height, which was 5. Therefore, I can make V1 the subject, and that will be the velocity just before collision. Okay, now I've got the one before collision and the one just after collision, meaning we can get change in momentum. But I want you to notice something. This velocity is upward, and this velocity is downward. What should we do? What we should do is to distinguish them by a change of sign. I think you remember, motion in opposite directions is distinguished by a change of sign. We saw that in video 2, which was about motion in a straight line. So now these ones are in opposite direction, meaning they should be distinguished by a change of sign. So you shall come and say, let upward velocity be positive and downward velocity be negative. When that happens, you can come and say, therefore, average force is change in momentum over T. M is mass. V is the final velocity, which is actually we need to change in momentum, so we can use this one. Final velocity is this at rebounding. Remember, it was this at rebounding and this one going before collision. Then the initial velocity is this. But I think realize we have distinguished the two by a change of sign. Upward was positive, downward was negative here. So when this negative is missing, the answer will never be correct. So you should always remember to distinguish opposite directions with a change of sign. Then T is that. Therefore, when I use a calculator, I'll come up with this as the value of the average force. That was question 1. What about question 2? Question 2 came from U.A.C.E of 1997, paper 1, question 2A. And it says, a ball of mass 500 grams traveling at a speed of 10 meters per second and 10 meters per second at 60 degrees to the horizontal, strikes a vertical wall and rebounds with the same speed at 120 degrees from the original direction. Okay? If the ball is in contact with the wall for 8 exponent negative 3 seconds, calculate the average force exerted by the wall. So we shall need to make a sketch. We shall draw our vertical wall and we draw the ball at this point. Then they said it is moving with this speed at this angle to the horizontal. So that will be the direction. and this will be 60 degrees with this. So alternating angles, this angle will be the same as this. Then they told us it rebounds with the same speed at 120 degrees from the original direction. So 120, we have already taken 60, so meaning the balance is 60 to make the 120. So this is the 120 degrees they talked about from the original direction. Same speed, that's why here there is 10 meters per second and here 10 meters per second. Now this one shows that we need the knowledge which we saw under vectors and scalars. So vectors and scalars, we learned something called resolving horizontally and vertically. So that is what we are going to use. So mass was 500 grams convert to kilograms, and U was 10. Time was that. Therefore, you come and say considering horizontal components of velocity. So horizontally, this initially it is going in this direction. Okay, and after it goes in this direction. That means that velocity to the right will be positive and velocity to the left will be negative. So this is the final velocity, it will be a negative. This is the initial velocity, it will be a positive. So I'll come and substitute for M, for V, and for U, and for the angle, then for T, and use a calculator to come up with this value. So it is negative, but it is okay. It shouldn't, this negative shouldn't scare you. What you need to do is to just come and conclude that the average force exerted by the wall is 625 Newton. That was question 2. Now we shall go to question 3. Question 3 says, a jet of water emerges from a hose pipe of cross-section area this with a velocity of 3 meters per second and strikes a wall at right angles. Calculate the force on the wall assuming water is brought to rest and does not rebound. Okay. So yes, still we shall need to make a sketch. So this is the water striking and this is rebounding. Rebounding, they said it doesn't rebound, that is why we give it 0 velocity. So this is what we know, that initial velocity is that, area is that, and final velocity is that. Therefore, volume per second is equal to cross-section area times velocity. So cross-section area is this, velocity is that, to give you this as the volume per second. The aim of getting volume per second is to help us get the mass, because mass is density times volume. So if I want volume per second, I'll get volume. So if I want mass per second, I'll get volume per second times density. So volume per second is this. Density of water is a constant, which is 1000. This gives you that kilograms per second, and that is m over t. Then I will remember the formula that force is equal to change momentum over time. So m over t is already catered for by this. What is left is v minus u, which is here. So substitute for m over t, which is this, and change in velocity. There is this. Here there is change in direction, but still because this is 0, that's why it is okay not to put a negative. But if it was a value, we would distinguish it by a negative. So 0 minus the initial, and in the end you come up with negative 75. So that negative shouldn't scare you. What you need to do is to conclude that the force on the wall is 75 newtons. That was question 3. Now we shall go to question 4. Question 4 says, a factory waste pipe emits fluid of density 1200 kilograms per meter cubed through a pipe of cross-section area 25 centimeters. the fluid leaves the pipe horizontally with a speed of 5 meters per second and strikes a vertical wall without rebounding. Find the magnitude of the force acting on the wall. Assume that the wall is sufficiently close to the source to allow any change in velocity of the fluid between emission and impact to be neglected. So neglect the change in velocity. So we have density is that, area is that, and initial velocity is that, final velocity is that. So volume of water hitting the wall per second is cross-section area times velocity. I think you remember that in the previous question. Then mass of water hitting the wall per second, m/t is volume per second times density. So substitute for volume per second to give you AU rho. Therefore, force is equal to change in momentum over t. Now this m/t is catered for by this, which is this, and you remain with change in velocity, which is here. After which you shall substitute area, substitute for velocity, substitute for density, substitute for change in velocity to give you that as the force. So the magnitude will be 75 Newton. Question 5 says, during a water pistol fight, John squirts water into the face of Jacob. The water is emitted through a nozzle of cross-section area 1 millimeter squared and travels horizontally with a speed of 8 meters per second to hit Jacob's face at right angles without rebounding. Okay. Find the magnitude of the force acting on Jacob's face. Then in brackets they tell us to take density of water as that and assume that John and Jacob are sufficiently close to each other that the change in speed of water between emission and impact is negligible. So we have density, we have area, we have velocity initial and final. So final 0 because they told us it doesn't rebound. So we're going to still go through the same procedure. Volume of water hitting the wall per second. Volume per second is area times velocity. Then mass per second is volume times density. Therefore the force they want is given by this, so you substitute to get the answer they wanted. Therefore magnitude of the force is 0.064 Newton. So that was the first part in this topic, and that was about Newton's second law of motion. Remember, we have not yet gone through the Newton's third law of motion. We are still expanding Newton's second law. Now the second part in Newton's second law is about the relationship between force, mass, and acceleration. I know in your O-level you covered this relation, but still we have to go through it because it is also set in a level. So suppose a resultant force. I want you to know this word, resultant force. So F is not just any force. It has to be a resultant force. Okay? Acts on a body of mass m for a time t and changes the body's velocity from u to v. From Newton's second law of motion, F is equal to change in momentum over t. So I can rearrange to come up with that. Then I remember that from first equation of motion, when I make A the subject, it will be v minus u over t, which is similar to this. What does that mean? That means I can replace the whole of this with A to come up with the relationship between force, mass, and acceleration. So we shall use that to go through these questions. So this part requires knowledge of vectors and scalars. That's why I told you it is advisable not to skip topics. So watch the videos in the order given. So for by now I believe you have already gone through the video 3 of vectors and scalars. So I shall say question 1 will come from 2019, paper 1, question 1b, and it says a body of mass 0.2 kilograms at rest is acted on by 4 forces of 2.8 Newton, 6.0 Newton, 4.5 Newton, and 1.2 Newton as shown in figure. Calculate Roman 1, the resultant force on the body, and Roman 2, the distance moved in 4 seconds. So here we shall need to resolve. The first thing to do, I think remember, is to look for angles lying to the horizontal. So if we do that, this is what we are going to get. For example, this is 60. The balance to make 90 will be 30. That is why you put 30 there. And the whole this is 100. So 100 minus this 30 will give you 70. That's why you put 70 there. So with that, we can easily resolve. So resolving this 2.8 is resolved in that this is this to give you that. So by now I believe you know how to resolve. So I shall not over explain why this is negative, because we already explained that in detail under the video of vectors and scalars. So from that we shall need to draw a right angle triangle of positive horizontal and negative vertical. The line from start to end will be our resultant force, and this theta will be the direction. So the resultant force magnitude will be this, and the direction will be that. So here we used 4 decimal places, but it is advisable to use 2 decimal places. Therefore, the resultant force is that, and in the direction this, below the positive horizontal. That was Roman 1. Roman 2 says that distance moved in 4 seconds. So distance moved, we need to first get acceleration. So F is equal to ma. Remember we said F is resultant force. That's why we're using this. Then mass and acceleration. Then A will be that. So now that you have acceleration, we can use the second equation of motion. Initial velocity is 0, time is 4, A is that, time is 4. So that gives you the distance moved as 349.272. And that's what they wanted. Then question 2 came from U.A.C.E of 2018, paper 1, question 1d, and says 3 forces, these ones, act on a body of mass 0.7 kilogram, as shown in the figure below. Calculate the acceleration of the body. So still the first thing to do is to get the angles to the horizontal. So if the whole of this is 120 and this is 90, the balance will be 120 minus 90, which is 30. So with that, you can now resolve. So you shall come and resolve this. Gives that, this gives that, and this gives this. So on the add, we come up with this. Like I said, by now, I believe you are well versed with resolving. So we shall draw positive horizontal and also positive vertical. Then line from start to end is our resultant. And this is the direction of the resultant force. So we can now get the magnitude, which is 10.3781. Then also get the command so that F is equal to MA. Therefore, substitute for F, M, and make A the subject. So here, they said acceleration, meaning we need direction. Remember, acceleration is a vector quantity. So we also need direction, and therefore you can conclude that the acceleration is this in the direction this above the positive horizontal. Then question 3 came from U.A.C.E of 2007, paper 1, question 4a, and it says, a body M of mass 6 kilograms is acted upon by forces, these ones, as shown in the figure above. Find the acceleration of M. So the same procedure, we shall need to get the angles to the horizontal. So if this is 20, this will be 70 to make 90. If this is 40, this will be 50 to make 90. And with that, we can resolve. So resolving this gives that. Resolving 25 gives this. Resolving 30, resolving 20. In the end, we come up with this. So now shall draw our right angle triangle. Negative horizontal and positive vertical. And this will be the resultant, this is the direction. So I can get the resultant force to be that, and also the direction to be that. But F is equal to MA, therefore substitute for F and M to get the value of A. Then you can conclude, and that's what they wanted. So now we shall go to question 4, which came from U.A.C.E of 2022, that is last year, paper 1, question 2b, and it says, figure 2 shows acceleration time graph for a body of mass 10 kilograms, which starts from rest and moves in a straight line. Use the graph to find Roman 1, the distance traveled in 15 seconds, and Roman 2, the average force acting on the body over the 15 seconds. So this is an acceleration time graph. Here, the acceleration is 2 and the time is 5. Then here, the acceleration is 0 and the time is 10. So you come and see that for the first 5 seconds, acceleration is 2, time is 5, and initial velocity is 0. Therefore, using the second equation of motion, we can substitute for U, for A, and for T to get this distance. That is the first 5 seconds. What about, okay, then the velocity, it will be using the first equation of motion, U is 0, A is 2, T is 5, to give you this. So that velocity will help us to get the force. Then for the next 10 seconds, acceleration is 0, T is 10, U is 10. Therefore, using the second equation of motion, we can substitute to get 100. Therefore, total distance will be got by adding this to give you 125. Then for Roman 2, they want the average force acting on the body. Remember, we already looked at average force being equal to change in momentum over T. So we shall come and substitute for mass, for final velocity, initial velocity, and the time to give you that as the force. Okay, so that has been Newton's second law. Now we shall go to Newton's third law. Newton's third law states that action and reaction forces are equal but opposite. And the definitions we need, one will be weight. So weight is the product of mass of a body and acceleration due to gravity. So G is acceleration due to gravity, therefore weight is equal to mg. Therefore, if you know the mass in kilograms, you can get weight by multiplying by acceleration due to gravity. Some students confuse this G with grams, but that is not okay. G is acceleration due to gravity when you're getting weight. So the magnitude of G varies slightly at different places on the Earth's surface, but for purposes of calculations, it is taken as having a constant value. So for calculations, G will be taken to be 9.81. So a brick of mass 1.5 kilograms will therefore have a weight of 1.5 times 9.81 to give you this as the weight. So each time you have mass, multiply by acceleration due to gravity to get the weight of that particle. And one thing we need to know about weight is that it always acts vertically downwards, as shown in the figure. So if you have that body, then the weight will be downward. So each time you see a body having a mass, just know that it has weight as one of the forces acting on it. After weight, there's another force called reaction. So if a brick of weight, this, is placed on a rough horizontal surface, it exerts a weight onto the table. Okay? And when that happens, by Newton's third law, the horizontal surface also exerts a normal reaction, capital R, onto the brick, which is equal and opposite to the weight, as shown. So we shall have a horizontal surface with a mass. The weight will be acting vertically downwards. So for this one to be equal and opposite, it must act vertically upwards. Okay, so now you have seen so far two forces, weight and normal reaction. So next force will be friction. So if a brick is placed on a rough horizontal table, note this word rough, and a person tries to push it along as shown, it has to exert a force in order to do, so. So this implies that there is a resistance to the person's push, and this resistance is known as frictional resistance. So let's try to illustrate. We have a horizontal surface which is rough and a brick which has a mass. So one, we saw because there is a mass, there should be weight. Two, because the brick is resting or lying on a horizontal surface, that horizontal surface should react. So that is where normal reaction comes from. And three, because the surface is rough, there should be opposition or resistance to a push. So if you have a push, there will be a resistance in the opposite direction. One thing you need to note is that this friction acts in a direction opposite to the motion of the particle. And it always occurs, is always present whenever the surface is rough. When they say the surface is smooth, it implies there is no friction. But each time you read the question and they say that the surface is rough, you should have it in your mind that friction will be one of the forces acting on that particle. So that acceleration shows the direction of motion of the particle. So by definition, friction is the force which opposes relative motion between two bodies in contact with one another. And what you should notice is that since this type of motion is in a straight line, then the three equations of motion can also be used where necessary. So the first equation we saw as that, second is that, and third is that. So these ones can also be used alongside Newton's equations of motion, Newton's equations from which is F equal to ma, which comes from the second law. So with that, we can go through these questions. Question 1, a force of 15 Newton acts on a mass of 5 kg resting on a smooth horizontal surface. What is the acceleration produced? So shall need to illustrate. Surface, then the particle, then shall put the weight because there is a mass. So it was 5 kg, it will now become 5g Newton. Then the normal reaction, because there is weight, there should also be normal reaction. Okay, now here they said it is smooth, meaning there is no friction. What is there is only the pulling force, which is 50 Newton. And the direction of motion will be in the direction of the pulling force. Therefore, resolving parallel to the plane. Parallel is this, horizontally. So resolving parallel to the plane, F is equal to ma, and F is the resultant force. In this case, there is only one force, so that's what we shall put here. And mass is 5 kg. Therefore, A can be got as 10 meter per second. And that's what they wanted. Question 2 says a mass of 5 kg is dragged across a rough surface. Frictional force equal to 3 Newton opposing the motion. Okay. By a horizontal force of 30 Newton. What is the acceleration produced? Now in question 1, it was smooth, but now it is rough. And they've given us the friction, which is opposes motion. Therefore, shall come and say that the surface is there, the particle is there, the weight, the normal reaction, the pulling force, the direction of motion, and because friction opposes motion, it will act in the opposite direction to that of motion. Okay, therefore shall come and say that resolving parallel, F is equal to ma. Now there are two forces. We need to get the resultant in the direction of motion. So it will be 30 minus 3, resultant force. Then m is 5. Therefore, you can get the value of acceleration which they want. Question 3 says find the constant horizontal force which would give a body of mass 5 kg at rest on a smooth horizontal plane a velocity of 10 meter per second in 4 seconds. So V is equal to U plus e.t. That is the first equation of motion. Substitute for V, for U, and for t. Then you can get the acceleration. Now after getting the acceleration, we can now illustrate. Weight, normal reaction, pulling force, acceleration. It is smooth, so there's no friction. That we shall resolve parallel to the plane. F is equal to ma. So mass is that, A is this, to give you that as the force they wanted. Find the constant force necessary. I think you'll see the questions are arranged in such a way that they will give an option for smooth surface and also for rough surface. So question 4 is now rough. So it says find the constant force necessary to accelerate a car of mass 1000 kilograms from this to this in 10 seconds against a resistance of 270. So you come and first use this first equation of motion to get the acceleration. Then we shall illustrate. Put the weight, put the normal reaction, put the pulling force, put the acceleration and then the friction or resistance to motion. Then we can now resolve part of the plane. Remember, resultant force is now F minus 270 equal to ma. Substitute for mass and for acceleration, and then make F the subject. And that's what they wanted. Question 5. A force of 25 Newton is applied at an angle of 60 degrees to the horizontal to a mass of 5 kilograms on a smooth horizontal table. What is the acceleration of the mass? So you come and illustrate. So put the weight, put the normal reaction. So now the force is at an angle to the horizontal. It is smooth, so there is no resistance. So we shall resolve vertical, horizontal and vertically. Then show the acceleration. Now we can resolve part of the plane. Now this, we don't use this. We shall use this horizontal component. So F equal to ma will be 25 cos 60 equal to 5a. Then make a the subject. That was the smooth surface. What if it was rough? So question 6 says, a mass of 2 kilograms at rest on a rough horizontal table. A force of 20 Newton is applied to the mass, the force making an angle of 30 degrees with the table. The frictional resistance is equal to 5 Newton. What is the acceleration of the mass? So we shall come, illustrate, weight, normal reaction, then the force at an angle to the horizontal, resolve it horizontally and vertically, then the acceleration and the resistance which opposes motion. Then you can resolve part of the plane. So we shall now use this force and this force to get the resultant force equal to ma. Then make a the subject. And that's what they wanted. So now we have been talking about friction, resistance, and now we are going to learn about a new term which is called coefficient of friction. So suppose a horizontal force F1 is applied to a body of weight W resting on a rough horizontal table as shown below. So we shall come and draw a table horizontal, then the body of weight W. Because of weight, there will be normal reaction, and there will be a force pulley which is acting. Okay. So the body does not necessarily move. And 2, the normal reaction of the table on the particle is the same as the weight. I think we saw that in Newton's third law of motion. Then you also see here there is friction. So there is friction force that opposes motion, or that opposes the applied force. So applied force in this direction to the right, friction is to the left. Just as we already seen that friction opposes motion. But our interest is to get the value of, is to get this thing called coefficient of friction. Okay, so you can see that this frictional force increases as applied force increases until it reaches a maximum value F, beyond which it cannot increase. So this maximum value of the frictional force is called limiting friction. And from experiments, we obtain a constant ratio of limiting friction to normal reaction. So limiting friction over normal reaction is constant. So let's try to show it here. Limiting friction over normal reaction is constant, and this constant quantity is denoted by Greek letter mu, and that is what we call coefficient of friction. So coefficient of friction is the ratio of limiting friction force to normal reaction. Therefore, we can now confidently come and substitute. Limiting friction is F, normal reaction is capital R, and this constant will now be mu, which is coefficient of friction. When I cross multiply, take this R this side, I'll come up with F being equal to mu R. So this is now a new formula that each time they give coefficient of friction, you can get friction by multiplying mu coefficient of friction by normal reaction. Another term they usually use is called angle of friction. Angle of friction is arctan of the coefficient of friction. So when you have the coefficient of friction, arctan of that coefficient of friction gives you what we call the angle of friction. So with that, we shall now consider various cases of motion. And the first part will be motion on rough horizontal surfaces. So we shall consider particle of mass m, kilograms, at rest on a rough horizontal plane. If a horizontal force F1 is applied on the particle and the particle moves with an acceleration a on the rough surface, the forces acting on the body are as shown below. So we need to draw a horizontal surface and the body. One, because there is weight, because there is mass, there should be weight. And because this weight is relying on the surface, there should be normal reaction. Okay, then they also talked about a horizontal force here, which is pulling, so that is F1. Then that force pulling causes the particle to move in this direction. So the direction of motion is denoted by acceleration. Okay, and because the motion is in this direction, friction will oppose the motion. So it will act in the opposite direction. This friction is there because they told us that the plane is rough. If it was smooth, friction would not be there. So resolving perpendicular to the plane is the same as resolving vertically. Upward force is equal to downward force. So you come up with R equal to mg. What about resolving parallel to the plane? We know that forces to the right are equal to forces to the left. So F1 is equal to mu R. Now this mu R is this, remember F, we saw that F is equal to mu R. So we have substituted for F. So this, the resultant force is equal to MA. So here, just like it was before, even in this case, the equations of motion can be used. So with that, we shall go through these questions. Question 1. When a horizontal force of 14.7 Newton is applied to a body of mass 4 kilograms, which is resting on a horizontal rough plane, the body is found to be in limiting equilibrium. Calculate Roman 1 the coefficient of friction between the body and the plane, and Roman 2 the angle of friction. So shall first illustrate horizontal surface, the body, there should be weight, there should be normal reaction, there should be pulling force, which is this, then the direction of motion, which is A, equal to 0. A equal to 0 because it is in limiting equilibrium, it is just at the point of moving, and friction because it is rough. It is rough, and therefore friction must oppose motion. So resolving vertically, this will be equal to this, to give you that. Therefore R is 39.24. What about resolving horizontally? This will be equal to this. So this will be equal to that. So here it is okay to still use this, But you can also say this is equal to this because this is 0. But to be clear, let's use the format we know, that resultant force is equal to ma. Then we shall come and substitute for a as 0 and r as 39.24. Therefore, this will now be equal to that, to give you the value of mu as 0.375. Roman 2, the angle of friction. Now that we know mu, the angle of friction will be arctan mu, which will give you this. That was question 1. Question 2, a body of mass 0.4 kilograms is at rest on a horizontal surface. If the coefficient of friction is 0.5, find Roman 1, the angle of friction, and Roman 2, the magnitude of the least force that will move the body along the surface. So we shall need to illustrate horizontal surface, the body, put the weight because it has mass, then normal reaction, the pulling force, which is now least force, that's why we put F min to mean minimum force. Then the direction of motion and the friction. Then we shall come and say angle of friction is arctan mu. The good thing we already know the coefficient of friction, so substitute to get the angle of friction. Roman 2, they want the value of F min. So first of all, resolving vertically, r is equal to 0.4 g. Substitute for g to get the value of r. Then horizontally, F min minus mu r is equal to 0 because the acceleration is 0. Therefore, F min will be mu times r to give you this. And that's what they wanted. Then question 3, a particle of mass 2 kilograms resting on a rough horizontal plane is pulled by a force of magnitude 11.3 Newton, inclined at an angle of 60 degrees to the horizontal. If the particle does not move, find the maximum value of the coefficient of friction between the particle and the plane. So still here I shall need to illustrate horizontal surface, the particle, then the weight, normal reaction, then the pulling force which is acting at an angle. Then resolve horizontally and also vertically. Then put the acceleration which shows the direction of motion and the friction which opposes motion. So resolving vertically, now here vertically we have this r and we also have this one. Down, those two will be equal to this. So r plus this is equal to 2g. Then substitute for g and make r the subject. So that will be the value of r. Then now resolving horizontally, we have this minus this equal to ma, which is 0. So substitute for r and get the value of mu as that. So that's what they wanted. Question 4 says a boy pulls a box of mass 20 kilograms by means of a light inextensible string attached to it across a rough horizontal ground. The coefficient of friction between the box and the ground is 0.25. If the string is inclined at 30 degrees to the horizontal and the box accelerates at 2 meters per second, find the tension in the string. So shall first illustrate the particle has weight, then normal reaction, then the force, pulling force acting at an angle, then resolve it, then show the direction of motion, and lastly friction. So shall first resolve vertically, there will be this and this equal to this. Okay, substitute for g and get an equation. So r in terms of f. Then resolving horizontally, there is this minus this equal to ma, where a is 2. So you come and write, substitute for r, substitute for a. So here we have only f as the only unknown. So expand, simplify, and make f the subject. And that's what they wanted. So that f is the tension in the string. That was motion on rough horizontal plane. What if a plane is inclined, but with no external force acting? So we shall consider a mass, m kilograms, moving downwards with a constant acceleration a on a rough plane inclined at an angle of theta to the horizontal. The forces acting on the body are as shown, so we shall first draw an inclined plane. That will be the mass. Then, because there is mass, there should be weight which is vertically downwards. Okay. Now, this weight can be resolved. Now, previously, for horizontal planes, we have been resolving vertically and horizontally. And vertically was perpendicular to the plane, horizontally was parallel to the plane. Now here we have strict, it has to be parallel to the plane and perpendicular to the plane. I think you see part of the plane is no longer horizontal. So we shall resolve part of the plane, resolve this one to give you mg sine theta. How does it come about? Then this will be mg cos theta. So this angle is theta, meaning this remaining angle will be 90 minus theta, and this will be theta. Okay, so where the angle lies becomes cos, and where it doesn't lie becomes sine. So what you should know is that always the component of weight parallel to the plane will be sine theta, will have sine, and the component of weight perpendicular to the plane will have cos, always. So normal reaction, normal means perpendicular to the plane. So previously it was vertical because the plane was horizontal. Now it is at an angle, it must maintain the 90 degrees. Okay, so this line is a straight line with the component perpendicular to the plane. So they said it is moving downwards, that's why acceleration is pointing downwards. And they said it is rough, meaning there should be friction, which opposes motion. Motion is in this direction, friction must oppose the motion. So there is no external force acting, therefore shall resolve perpendicular to the plane. Perpendicular means r will be equal to mg cos theta. Then parallel to the plane, we have this minus this equal to ma. And those are the two main equations. The rest is to remember that the three equations of motion can also be used. So with that, we shall go through some of the questions. So question 1 came from U.A.C.E of 1993, paper 1, question 1c, and it says, a car of mass 500 kilograms moves from rest with the engine switched off down a road which is inclined at an angle of 49 degrees to the horizontal. Calculate Roman 1, calculate the normal reaction, and Roman 2, if the coefficient of kinetic friction between the tires and the surface of the road is 0.32, find the acceleration of the car. Now we see another word, kinetic friction. Kinetic friction means the friction when the particle is moving. Then limiting friction is when it's not moving but just at the point of moving. But because at limiting friction is already the maximum value, it means that even when the particle is moving, it moves at the point of friction remains the same. So here we shall need to illustrate. This is the angle 49. Then the weight must act vertically downwards. Then from there, remember to resolve parallel to the plane. Like I said, it will always be sine. Then perpendicular to the plane will always be cos. Always. Then normal reaction to be in line with this component. And it is no longer vertical. Okay. Then it moves downwards with this acceleration. Therefore, friction must oppose motion. Then shall go through the same procedure, resolving perpendicular. This will be equal to this. Okay, they substitute for G to get this as the value of R. Then resolving, that is normal reaction Roman 2. If the coefficient of kinetic friction between the tires and the surface of the road is this, find the acceleration. So we are going to resolve parallel to the plane to give you that. It gives this minus this equal to MA. Then substitute for G, substitute for mu, substitute for R to get the value of A. So simplify and the value of A will be that. Question 2 came from U.A.C.E 2010, paper 1, question 3D, and it says, a body slides down a rough plane, inclined at 30 degrees to the horizontal. If the coefficient of kinetic friction between the body and the plane is 0.4, find the velocity after it has traveled 6 meters along the plane. So still shall need to make a sketch. Now these sketches or force diagrams are drawn using a ruler. So first is weight vertically downwards, then the component of weight parallel to the plane, perpendicular to the plane, then normal reaction and the acceleration, then the friction. So that the forces next is to resolve. So parallel to the plane, we shall come up with A this minus this equal to MA, which is the statement. Then substitute for G, for mu, and for R. R, remember we said R is mg cos theta, which is this. So m is constant throughout, it can cancel. So with that we can get the value of A. And that's what they wanted. So they wanted velocity also. So velocity shall use third equation of motion since we know the acceleration now. So acceleration, and we know the distance, and we know the initial, which was 0. So we can get the final velocity. So that was motion on inclined planes with no external force. What if there is an external force? So consider a particle of mass m kilograms at rest on a rough plane, inclined at an angle theta to the horizontal. If an upward force F1 parallel to the plane is applied to the particle and the particle moves with an acceleration A, the forces acting on the particle are as shown. So we shall draw our diagram using a ruler, put the weight, resolve the weight parallel to the plane and also perpendicular to the plane. Then normal reaction. Now here they say there is a force pulling, so put a force pulling F1. That means that now the particle will move upwards. And because it moves upwards, friction will act downwards. So we shall now resolve perpendicular to the plane. Resolving perpendicular to the plane will give R equal to mg cos theta. Then resolving parallel to the plane, this will be equal to the sum of these two, equal to this minus this equal to MA. So those are the two equations can be used, and also the three equations of motion are applicable. So question 1 came from U.A.C.E 1996, paper 1, question 2C, and it says, a car of mass 1,000 kilograms climbs a track which is inclined at an angle of 30 degrees to the horizontal. The speed of the car at the bottom of the incline is 36 kilometers per hour. If the coefficient of kinetic friction is 0.3 and the engine exerts a force of 40,000 Newton, how far up the incline does the car move? So you'll need to make a sketch. Weight will always be vertically downwards, then the component parallel to the plane always be signed, perpendicular to the plane always have cos, normal reaction, then there is a force pulling. That means the particle moves upward. And there is the friction opposes motion. Therefore, shall resolve parallel to the plane. It will be this minus these two equal to MA. So we shall come and write that. Then substitute for G, for mu, for R. Remember, R is this, which is the whole of this, is equal to mass, which is 1,000 times acceleration. Simplify and make A the subject. So now that I've got acceleration, we shall first change the initial speed from kilometers per hour to meters per second. Then we shall use second equation of motion to get the distance required. Question 2 came from, says, a particle of mass m kilogram is projected with a velocity of this up a rough plane of inclination 30 degrees to the horizontal. If the coefficient of friction between the particle and the plane is 0.25, calculate how far up the plane the particle travels. So I need to make a sketch. So I think I realized that there's no way we can run away from the sketch. Then show the weight, resolve part of the plane, perpendicular to the plane, normal reaction, pulling force is zero because they didn't talk about any force which is pulling, but they just said it is moving up. So this is the direction of motion, and friction opposes motion. So resolving part of the plane, it will be this minus these two equal to MA. So you come and put it there. Substitute. Simplify. So here we have substituted 0.5. So M cancels throughout. So here we have 0.25. You have G, cos that is that. Therefore, A can be got. It is a negative, meaning there is deceleration. So third equation of motion, we can get the value of S as that. And that's what they wanted. Question 3, a toy engine of mass 350 grams exerts a driving force of 0.1 Newton. With what acceleration could it climb a smooth slope of 1 in 10? So here the new word we are seeing here is 1 in 10, slope of 1 in 10. What does it mean? It means arc sine theta is equal to 1 over 100. Therefore, theta will be 0.58. Having got the angle, we can now draw our inclined plane. Then we shall show the weight. Resolve it part of the plane and also perpendicular to the plane. Then normal reaction. then the pulling force, acceleration show the direction of motion, and lastly the frictional. So here there's no friction because the engine of that's okay, they said smooth, so there's no friction. So shall resolve part of the plane. This minus these two is equal to MA. That means I can get the value of A. And that's what they wanted. So now shall go to another part called Pulley systems. And here we shall consider two particles connected by a taut. So this is a word means used to mean tight. So the objects are not directly in contact but exert equal and opposite forces on each other by means of the equal tensions. Note this word, tensions have to be equal in the string which act inwards at each end as shown below. So shall say that there is one particle, there's a second particle connected by the string. So because the string is tight, there will be tension. And what you should notice is that 1, the arrows are facing each other, and 2, the values of tension are the same. So if you draw something like this, it is not okay because they are facing away from each other. If you draw something like this, it is also not okay. Something like this, it is also not okay. So they must be facing each other. And this is true even if the string passes round a smooth body such as a pulley, and that is our interest. So let's try to show it here. We shall come and draw a pulley. So A and B are particles. Because they have mass, they will have weight. So weight is always there each time you see a mass. So we have mass A, there is weight. Mass B, there is weight. Okay, then you shall remember that tensions in the two portions of the string are the same at each portion, and each portion exerts an inward pull on each other. In other words, the arrows must face each other. So here they are facing each other, even this side, they will face each other. So in each portion of the tension at one end acts on the particle, and at the other end the tension acts on the pulley, and all these tensions are equal. So all of them are equal. And 2, this one acts on the pulley, this one acts on the particle, this one acts on the pulley, this one acts on the particle. So when the system is released, one particle will move upward, another one will move downward. And usually, the one which is heavier moves downward, and the one which is lighter moves upward. Now let us say that particle B is heavier than particle A. That means particle B will move downwards, and particle A will move upwards. Let's try to illustrate that. So I think we realize this particle is moving downwards and this one is moving upwards. So the direction of motion, like we have always done, will be represented by acceleration. So you come and put a downward acceleration on particle B and then upward acceleration on particle A. Okay. So there are some things you need to note. One is that because the string is inelastic, the distance B moves down is equal to the distance A moves up. That is 1. 2, the downward acceleration of B is equal to the upward acceleration of A. So I think you see here there is A, and also here there is A. It's a magnitude. It is only the direction which is changing. And 3, the downward speed of B is equal to the upward speed of A. So those 3 have to be remembered each time you're dealing with connected particles with an inelastic string. So to analyze the motion of the system, forces acting on each particle must be considered separately, and the equation F equal to ma applied at each particle in turn. So we shall start with particle A. If you look at particle A, we shall come back here. Remember these are the forces of particle A. So it will be upward, meaning it will be T, resultant force will be T minus M1G equal to MA, M1A. Therefore, we shall come here and write that using F equal to MA, resultant force is T minus M1G and mass is M1. So that gives you that equation. What about for particle B? For particle B, these are the forces. And it's downward, meaning the resultant force will be M2G minus T equal to M2A. Therefore, we shall come here and write our equation. Okay. So with these two equations and the three more equations of motion, we can easily answer the questions that proceed. So let's start with this question 1. Question 1 says, two particles of mass 4 kilograms and 3 kilograms are connected by a light inelastic string passing over a smooth fixed pulley. Find the acceleration of the particles and the tensions in the string when the system is moving freely. So you come and illustrate. Then you shall put the masses. One will have 3 kilogram mass and the other one will be 4 kilogram mass. So this 3 kilogram mass has tension also here, and this 4 kilogram mass also makes this to have tension. Remember, so tension arrows must face each other. Then in this part, 4 is heavier, meaning it will have a downward acceleration, and 3 is lighter, it will have an upward acceleration. Then for the 3 kilogram mass, it is moving up, so it will be T minus 3G equal to 3A. Substitute for G to get equation 1. For the 4 kilogram mass, we use these forces. It is downward, so it will be 4G minus T equal to 4A. Substitute for G and get equation 2. So now we have 2 equations and 2 unknowns. We need to solve them simultaneously. So equation 1 plus equation 2 will give us that. This is equation 1. This is equation 2. So when we add, this T will cancel. Then this minus this will give you this. And this plus this gives you that. Therefore, A will be equal to 1.401 meter per second squared. And that's what they wanted here. Then they also wanted that tension. For tension, use either equation 1 or equation 2. If we use equation 1, we shall substitute for A and simplify to get the value of T. And that's what they wanted. Then question 2, a light inextensible string passes over a smooth light pulley and masses of this and this are attached to its end. The masses are released from rest when the 7 kilogram mass is 1 meter above a horizontal table. Find the acceleration of the system and the tension in the string. So we shall first illustrate, put the weight, the tensions acting inward, then the weight and the tension acting inward. Then the acceleration, 7 is heavier, it goes down, 3 is lighter, it goes up. So for the 3 kilogram mass, these are the forces. It is upward, so it will be T minus 3G equal to 3A. Substitute for G and get equation 1. Then for the 7 kilogram mass, it is heavier, so it goes downwards. That would be 7G minus T equal to 7A. Substitute for G and get equation 2. So these are two equations and two unknowns, so we shall solve them simultaneously. So equation 1 plus equation 2 will give you that. So here, this will cancel with this, and this minus this gives this plus this gives you that. So in the end, A will be that. And they also wanted the tension, so use either equation 1 or equation 2. Using equation 1, substitute for A and make T the subject. And that's what they wanted. So that was a Pulley system. What if we modify a bit? So now we shall go to motion of connected particles and horizontal planes. So this involves the knowledge of forces on a particle lying on a horizontal plane. I think we did that earlier, and the tension in the string connecting the two particles. So question 1, a mass of 8 kilograms rests on a smooth, now it is smooth meaning there's no friction, smooth horizontal table connected by a light inextensible string passing over a smooth pulley at the edge of the table to another mass of 6 kilogram hanging vertically as shown below. When the system is released from rest, with what acceleration do the masses move, and what is the tension in the string? So first we need to redraw the diagram so that we can show the forces acting on the particles. So we have those particles. Then we can show the forces. Each time there is mass, there must be weight. So this is 8g to the mass was 8 kilogram. Because of this, there will be no more reaction here. Then for this, the mass was 6 kilograms, so it will be 6g. Then the tensions, arrows must face towards each other. Arrows must face towards each other. So this plane is smooth, meaning there's no resistance. When released, this will move downwards and this will move to the right. So with that, we can go through the F equal to ma. So for the 8 kilogram mass, the forces on the 8 kilogram mass are these ones. So it is T minus 0 equal to 8a. So that gives you equation 1. Then for the 6 kilogram mass, the forces are these ones. So it is 6g minus t equal to 6a. Then substitute for g. And so we have substituted for g to get equation 2. Then we shall solve them simultaneously. So substituting equation 1 into equation 2, where there is t, put it there. You'll come up with that. Then make a the subject, and that will be the acceleration. Then use either equation 1 or equation 2 to get t. So if I use equation 1, I'll come up with t as this. That was question 1. Question 2. So shall be dealing with smooth and rough particles, smooth and rough surfaces concurrently. So question 1 was in a smooth surface. Now this one is a rough, same setting, but this time round it is rough. So a particle of mass 3 kilogram is held on a rough horizontal table connected by a light inextensible string which passes over a smooth pulley at the end of a table to a particle of mass 2 kilograms which hangs freely as shown. If the coefficient of friction between the particle and the table is 1/3 and the particles are released from rest, calculate Roman 1, their acceleration, and Roman 2, the tension in the string. So still we shall need to redraw the diagram. That is the surface with the pulley. Then we put the particles connected by a string. Then next we shall show the forces. One is the weight acting vertically downwards, and there will be no more reaction because of the weight. Then here there will be also weight. Then the tension in the string, arrows must face each other. Same applies to this, arrows must face each other. Okay, so when released, these two will move downward. and this will move to the right. And remember, this surface is rough, it must oppose motion. So if it is moving to the right, friction must be to the left. So you come and put our friction there. The next is to write the equations. So 3 kilogram mass, these are the forces. So it is this side, so it will be T minus mu R equal to 3A. So you come and write that. Then you substitute. Mu was the third, was given as a third. Then R is equal to this 3G, which is 3 times 9.81. Then equal to 3A. Simplify to get equation 1. Then for the 2 kilogram mass, the forces are these ones. Downward it will be 2G minus T equal to 2A. Then substitute for T to get, substitute for G to get equation 2. Now those are 2 equations, 2 unknowns we need to solve simultaneously. So equation 1 plus equation 2 will give us that. So this and this cancels, this minus this gives this, and this plus this gives you that. In the end, we shall make A the subject, and that will be the acceleration. What about, let me see part Roman 2. Roman 2, they want the tension in the string. So tension, we use any of the 2 equations, either equation 1 or equation 2. If I use equation 1, substitute for A and make T the subject. And that's what they wanted. Okay, then equation 3, a mass of 12 kilograms rests on a smooth horizontal table. Okay, it is connected to 2 other masses. Note this word, 2 other masses. So the previous 2 settings, it was 1 mass connected to 1 other mass which is hanging. But now there are 2 other masses of 10 kilogram mass and 8 kilogram mass by a light inextensible string passing over 2 smooth pegs. Pegs in math, it means a circular surface fixed at the opposite edges of the table. Initially, the 10 kilogram mass is 0.8 meters below the level of the table, and the 8 kilogram mass is on the ground. Okay, given that the system is released from rest, determine Roman 1 the common acceleration, Roman 2 the tensions in the strings, and Roman 3 the velocity with which the 10 kilogram mass hits the ground if the ground is 2 meters below the surface of the table. So still, first we shall need to illustrate. Then we shall come and put the masses connected to 2 other masses. Okay. Then now we shall put the forces. First is the weight. Here it is 10 kilogram, the weight is 10G, and the tensions will act inward towards each other, facing each other. Okay. Then here they also face each other. Then for this mass, there's weight, and because of this weight, there is no more reaction. Then here there is now weight 8G, and here there will be tension. Now these are different strings. This was one string, this is another string. That is why tension here is different from the one here. So still they must face each other, and also here they must face each other. Okay, then if released, the one which is heavier will move downward, and this one will move upward. So automatically this one must move to the left. Okay, and they told us, let's see, here they said it is smooth, so there is no friction. Okay, so that means the forces are done. Now we shall need to use F equal to ma. So for the 12 kilogram mass, these are the forces acting. That what will be T1 minus T2 equal to 12A. For the 8 kilogram mass, These are the forces acting. So it will be T2 minus 8G equal to 8A. Substitute for G and get equation 2. Then for the 10 kilogram mass, these are the forces acting. So it will be 10G minus T1 equal to 10A. So substitute for G and get equation 3. So these are 3 equations and 3 unknowns, meaning we need to solve them simultaneously. So equation 2 plus equation 3 will give us that. So this is here, then this minus this gives you that. This plus this gives you that. And that will be equation 4. Then equation 1 plus equation 4 will give us that. So this cancels with this cancels with this, will remain with this here, and this plus this gives that. So in the end I can get the acceleration. That was Roman 1. What about Roman 2? Roman 2, they want the tension in the strings. So from equation 3, we can substitute for A and get the value of T1. Okay. What about from equation 2? Substitute for A to get the value of T2. And that was Roman 2. Roman 3, they said the velocity with which the 10 kilogram mass hits the ground if the ground is 2 meters below the surface of the table. But they talked about something here. They said 10 kilogram mass is 0.8 meters below the level of the table. So you come and see that initial velocity is 0 because they were just released. Acceleration, you have got it. And the distance will be the difference. So 2 minus 0.8 gives you 1.2. Therefore, I can use the third equation of motion, substitute to get the value of V. And that's what they wanted. Then question 4. Now question 4 is similar to question 3, only that now this one, it is rough. So as we shall see, so that it came from UNEB of 1998, November, paper 1, question 2C, and says the diagram in the figure below shows 3 masses connected by inextensible strings which pass over frictionless pulleys. The coefficient of friction between the bench and the 12 kilogram mass is 0.25. As you can see here. If the system is released from rest, determine Roman 1, the acceleration of the 12 kilogram mass, and Roman 2, the tension in each string. So first you need to redraw in order to show the forces on the particles. So you now put the particles. Then shall now show the forces. Here it was 1.3 kilograms, so it will be, weight is 1.3 G. Here arrows must face each other. Then same applies to this, they must face each other. Then here the weight will be 12 G, and because of the weight there will be normal reaction, R. Then here the weight will be 6.7 G, and here the tension, it is different from this, so it will be T2 arrows facing each other. Same applies to here, T2 arrows facing each other. Then this is heavier than this, so it will be downwards, this will be upward, and automatically this will be to the right. Okay, it was rough, so there should be friction. So Roman 1 shall say for the 1.3 kilogram mass, the forces are these ones. So it will be T1 minus 1.3 G equal to 1.3 A. substitute for G to get equation 1. Then for the 6.7 kilogram mass, these are the forces. So it will be 6.7 G minus T2 equal to 6.7 A. Substitute for G, and that will be equation 2. So that is the 1.67 kilogram mass. What about the 12 kilogram mass? For the 12 kilogram mass, these are the forces of interest. So it will be T2 minus these 2 equal to 12A. That we shall come here and say that for the 12 kilogram mass, T2 minus T1 plus mu R is equal to 12A. Then you substitute for mu, substitute for R, which is mg, which is 12G, equal to 12A. Simplify to get equation 3. So the 3 equations, 3 unknowns. Next is to solve simultaneously. Equation 1 plus equation 2 will give us that as equation 4. Then equation 3 plus equation 4 will give us that. And from that we can make A the subject. And that's what they wanted. So what about Roman 2? For Roman 2, they want the tension in the string. So use any of the, we have to get T1 and T2. So we can use equation 1 to get T1. So substitute for A and get T1. Then equation 2 can be used to get T2. Substitute for A and get T2. And that's what they wanted. So now we shall go to motion of connected particles and inclined planes. We have been dealing with horizontal planes. Now we shall go to inclined planes. So still this involves knowledge of forces on a particle lying on an inclined plane, which we have already covered, and the tension in the string connecting two particles. So question 1 says a mass of 12 kilograms rests on a smooth plane, inclined at 10 degrees to the horizontal. The mass is connected by a light inextensible string which passes over a smooth pulley fixed at the top of the plane to a mass of 4 kilograms which is hanging freely as shown. With the string tight, the system is released from rest. Find Roman 1, the acceleration of the system, and Roman 2, the tension in the string. So first we need to redraw the given diagram so that we can be able to show the forces. So that's the inclined plane, that is the masses. Okay, then we shall show the forces. First is weight, of course, acting vertically downwards, and this component part of the plane is this, component perpendicular to the plane is that. Then the normal reaction is capital R. Then the tension arrows must face each other. Here the weight will be that, and the tension arrows must face each other. The plane is smooth, so there is no friction. So when released, now here, how do you know which goes down? Of course, this compare 4G with this and see which one is heavier. So this is heavier, so it goes down, and this goes up. Then we shall start for the 12 kilogram mass. We are interested in these forces. Those ones. So it will be T minus this equal to 12A. Then substitute for G and get equation 1. What about for the 4 kilogram mass? We are interested in this, which is 4G minus T equal to 4A. Substitute for G and get equation 2. Those are 2 equations, 2 unknowns we need to solve simultaneously. So equation 1 plus equation 2 will give us this, where A can be made the subject to get the acceleration. Then for Roman 2, they want the tension in the string. So from equation 1, you can either use equation 1 or equation 2. So from equation 1, substitute for A and get the value of t. And that's what they wanted. Question 1 was for smooth surface. What if the surface is rough? So that is what question 2 will answer. So a body A of mass 20 kilograms lies on a rough plane, inclined at an angle theta to the horizontal, where sine theta is equal to 1/2. The coefficient of friction between the plane and the body is 0.65. From A, a light inextensible string passes up the line of greatest slope and over a smooth pulley to a body B of mass 30 kilograms. If the system is released from rest, find Roman 1, the acceleration of the system, and Roman 2, the tension in the string, and Roman 3, the distance moved by A after 3 seconds, assuming that nothing impends the motion of either mass. So you need to first draw the force diagram. So the sine theta is equal to a half, meaning theta is 30. Therefore, we can now draw our diagram. Put the particles connected by a string. Then shall show the forces. First is weight and the component parallel to the plane, component perpendicular to the plane, and the normal reaction. Then the tension, arrows must face each other. Then the weight here, vertically downwards, and tension, arrows must face each other. So still this one moves downward because 30g is heavier than 20g sine 30. So this one moves downwards, this one moves upwards along the line of greatest slope. Then because of that, because this one moves upward, friction must oppose motion, so to be in this direction. Then you can start for the 20 kilogram mass. These are the forces. So it will be T minus these two equal to 20A. Then substitute for G, mu, and R to get equation 1. That is equation 1. What about for the 30 kilogram mass? For the 30, these are the forces of interest. So it will be 30G minus T equal to 30A. So shall come here and substitute for G and get equation 2. So 2 equations, 2 unknowns. Solve simultaneously. Equation 1 plus equation 2 will give us that, and make A the subject to give you the acceleration. Then from equation 1, we can get the value of T. That is Roman 2. Roman 3, the distance moved by A after 3 seconds, assuming that nothing impends the motion of either mass. So we shall use the second equation of motion, substitute for U, which is 0, A, which we have got, and T, which they have given us, to get this distance. And that's what they wanted. Then question 3, the diagram shows particles A and B of masses m kilograms and 10 kilograms respectively, connected by a light inextensible string passing over a smooth pulley. When the system is released, mass m is just about to slide upwards along the plane. Given that the coefficient of friction between the mass m and the plane is this, find the value of m. Now here the keyword is just about to slide upwards. meaning it is at the point of sliding, therefore acceleration is still 0. So we shall first redraw, show the particles, then the forces. There is weight here, then its component parallel to the plane, component perpendicular to the plane, normal reaction, then the tension, arrows facing each other, then the weight and tension, arrows facing each other. At the point of moving upwards, so it will have 0 acceleration, but acceleration will be up. That is why friction opposes motion. So for the 10 kilogram mass, we need these forces. So they are equal because it is not yet moving. So T will be equal to 10G and T will be 98.1. For the m kilogram mass, we need these forces. So T will be equal to these two. So come and substitute. Mu is that, G is that, sin is that. Sorry, mu R. Mu is this. Then R is mg cos theta. Then mg sin theta is this. Collect like terms and get the value of m. And that's what they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on work, energy and power. So if you're not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.